Today's video, we will be looking at the electrolysis of certain substances. Now that we understand the basic principle behind electrolysis and some terms, we can go now in more depth in looking at the electrolysis of various substances. The objectives that will be covered in this topic will include to discuss the electrolysis of certain substances using the three factors. These are position of ions in the electrochemical series, concentration of electrolytes, and the type of electrodes. We will identify the ions present in our electrolytes, after which we will predict the electrode to which an ion will drift. That is called migration. Then we will predict chemical reactions taking place, making use of the electrochemical series. Let us begin. Let's start by looking at the factors that determine preferential discharge. Now, during the electrolysis of aqueous solutions, only one ion can be selectively discharged at each electrode during the electrolysis. Now, you will have more than one ions going towards the anode or the cathode, but one will be preferentially discharged over the other. What do we mean by preferential discharge? We mean that an ion will form an atom or a molecule, and that will come off as a solid or a gas or even liquids. So when we say preferential discharge, which ion will change from ion to an atom in its free state or element in its free state? We discussed already the three factors in terms of what are they. They are positions, concentration, and the type of electrodes. We will start by looking at the position of the ion in the electrochemical series. Now, you should remember that we discussed already the electrochemical series in terms of what is taking place. Just to do a quick recap, remember the cations are all positive ions, and in order to form their element in their free state, they must gain electrons. Now, if they gain electrons, then these cations must be reduced. And by reduced, we mean that they are gaining electrons. The anions will be oxidized. Why are they oxidized? Because they are losing electrons. The trick is which one is oxidized more easier than the other. Now, we said that for the anions, oxidation increases down the series, whereas for the cations, reduction increases down the series here. So, in terms of the ions here, silver would come off or be preferentially discharged over lead ion, or copper would be discharged over hydrogen plus ion. In the case of the anions, hydroxide will be preferential discharge over Cl- because it is more easily oxidized than the ones above. And over here, these are more easily reduced down the series. So let's choose anyone. Let's choose zinc 2+, and we're going to add electrons because we are being reduced. And over here, we can use, we know that OH- would form H2O and O2, and we must balance this equation here. And so we can add 4 electrons here. And that would produce our water liquid and our oxygen gas. So I2 would not be oxidized, or I2 will not come off in preference to OH if OH ions are present, because OH is more easily oxidized. That is, it takes less energy. So simply put, the ones that are lower in the series will be preferentially discharged over the ones above. And the greater reason for that is that they are more easily reduced in the case of the cations, and in the case of the anions, they are more easily oxidized. One important point to note that when you are dealing with positions in the series, you must look out for the type of electrolyte. They will say the electrolyte is either dilute or aqueous. So that's in case of the electrolyte. The electrode must be inert, and that is carbon. You'll see carbon, you'll see graphite or platinum. So in terms of the electrolyte, it must be dilute, very dilute, or aqueous. And the electrode must be inert. Now, another important thing to note is that if you are aqueous or dilute, then you would contain a lot of water. Now, what are the ions present in water? Well, you have H plus and you have OH minus. Let's just look at a simple one here. Suppose I say the electrolysis of aqueous or dilute sodium bromide. So you'll see sodium bromide, and this is aqueous. What are the ions present? Well, we have Na plus from sodium bromide, and we have Br minus from sodium bromide. Then we have H plus from water, and we have OH minus from water. Now, these ions from water are plenty. So in terms of the position now, you would look to see where is the H with respect to the Na, or where is the OH with respect to the Br. Let's check to see if Na is below H or H is below Na. If you look in the series here, you'll see we have H plus here and Na here. That means that H plus will be more easily reduced than Na, hence H plus would come off in preference to Na. In case of the anions, OH minus is here and Br minus is here. Therefore, OH minus will be more easily oxidized than Br. Hence, it will come off in preference to Br. So, in the case of Na and H plus will be more readily reduced. Therefore, it will gain the electron to form H. So, H2 gas will come off in preference to Na solid. And over here, water and oxygen would be discharged at the anode, being the positive electrode. So the anions will move towards the anode and be discharged. So you'll observe effervescence coming off at the anode as well as effervescence at the cathode. Now we can move on to looking at the factor of concentration. In studying the concentration of ions in our electrolyte, there are some points we need to consider. We need to consider the first point, that the cations are treated the same way as the position in the series. So the cations, you will treat them the same way. That is, position in the series takes preference. However, now the anions, this is where the concentration would take effect. So when I say concentration, I am dealing mainly with the anions, not so much the cations. So for the cations, we will use position in the series, while the anions, if it is concentrated, then we look mainly at the anions. But more preferably, or more importantly, it deals with the halide ions. When we say concentrated, it means that we have a lot of the halide ions or the negative ions present over the OH that is present in water. So in this case, the anion would be plenty here, while the water or the OH in the water and the H plus would be in small amounts. So concentration means that we have a lot of Cl ions here in the case of concentrated sodium chloride. So you'll notice that we have the cations here, and over here we have the anions. But remember that we will treat the cations as the position in the series. So in the cations, if we're looking at the position it is in the series, then H would come off in preference to Na because H is lower than Na. In case now of the anions, because the Cl minus is in greater amounts because it is concentrated, now the Cl would come off in preference to the OH minus. So again, the second point is that the concentration deals mainly with anions, more specifically halide ions. And you know those are your Cl minus, your Br minus, and your I minus. So that is important. In terms of the electrolyte, it must be concentrated. And in terms of the electrodes must be inert. So these are the important things to look for. Now, in the event that H came off in preference to Na, then H plus would be reduced because it is on the positive side. So that would gain electron there and form H2. And of course, we need to balance this part here. And that's your aqueous ion, and that's your gas. So you should see effervescence if a gas is coming off. In case of OH and Cl, if it was dilute or aqueous, then OH minus would come off in preference to Cl minus. But it is not aqueous or dilute. It is concentrated. Hence, Cl minus would come off in preference to OH minus. So we will write the equation for Cl minus, and remember that oxidation is taking place on this side. So we will lose electrons. Remember that whenever we have oxidation, the electrons are placed on the right. So here we'll form Cl2. And of course, we must balance the equation here. And then we balance the ions by adding 2 electrons on the right. So you should observe effervescence at the cathode, and you should observe effervescence at the anode. Chlorine is a pale green gas. Just some important information you should know if you are making your observation. So as long as that gas is coming off, you should observe effervescence. And if you see a color, of course, you should note that color of that particular gas. In our case here, H2 is a colorless gas, while Cl2 is a pale green gas. Now, these gases coming off at the electrodes, you should know that we can test for these gases. We can test for H2 gas, we can test for Cl2 gas, we can test for O2 gas. As we go through, we will be discussing how to test for these gases. Let us move on and talk about factor 3, which is now dealing with the type of electrodes, whether it is active or inert. In terms of the nature of the electrodes, it means that if the electrode is active, then it will take part in the reaction. That is, it will react with the electrolyte. If the electrode is inert, then no reaction. Now, when do you have inert electrodes? When we are dealing with factor 1, which deals with position in the electrochemical series, or concentration of your electrolytes. Those two factors deal with the inert electrodes. Factor 3 deals mainly with your active electrode, and this is the one that will take part in the reaction. Now, the active electrode deals mainly with the anode. What is going on at the anode? The cathode can be inert, or it can be the same type of electrode that you put at the anode. But what is important is that the anode is the active electrode. So the cathode can be inert in terms of you can place graphite there or carbon or platinum. But if you are dealing with active electrode, you must put that electrode that is active at the anode. Now, what do we mean by that electrode is active? First of all, we must ignore all ions that is present in the electrolyte because this is not taking preference. The type of electrodes take preference to factor 1 and factor 2. So we are going to ignore ions present because the only thing that is going to take place at the electrodes is that at the anode it will dissolve and the cathode will be built up with whatever was dissolved at the anode. So the anode dissolving should get smaller while the cathode should get larger or increase in size. So remember now, dissolving takes place at the anode because it is now active and is taking part or reacting with the electrolyte. While the cathode, whatever was dissolved at the anode, it will be built up at the cathode. So let us look at some points about the active electrode. So as long as you are active, 1, you must be a metal that is a metal of the electrolyte. For example, if your electrode is copper, then your electrolyte must be copper 2 sulfate. If your electrode is silver, then your electrolyte must be silver nitrate. In other words, the electrolyte must be a soluble salt of the anode. So in this case, copper sulfate is your soluble salt of copper. Silver nitrate is your soluble salt of silver. So copper, in the case of copper sulfate, would be placed at the anode. And silver, in the case of silver nitrate, would be placed at the anode. So let us look at our reactions taking place at both electrodes. If you are active, then at the anode, the metal will simply dissolve to form metal ion. M is my symbol for my metal. Now remember that oxidation takes place at the anode. So my metal should be losing electrons. So in this case, my metal atom dissolved to form my metal ion. Now at the cathode, my metal ion is now being reduced to form back my metal atom at the cathode. So you see that the metal is dissolving at the anode, while at the cathode, my metal is being formed on the electrode that is the cathode. And what reaction takes place at the cathode? Reduction. Always. So you see here where we are gaining electrons, while here we are losing electrons. Now that we understand the 3 factors that determine preferential discharge, let us look at some examples now of the electrolysis of various substances. Let us start by looking at the electrolysis of aqueous copper 2 sulfate solution using inert electrodes. Now, what did I say the important points were? Well, you see this term, aqueous. It means that we must be looking at factor 1, which deals with the position in the series. So the important terms, 1, aqueous, 2, the electrode is inert. So then, what's important? Factor 1. How do we proceed? First thing we must do is to identify the ions present. In aqueous copper 2 sulfate, we have Cu2 plus ion and we have SO4 2 minus ion from copper 2 sulfate. Then we have H plus ion and OH minus ion from water. Now, because it is aqueous, we have a lot of H plus and OH minus ions present. The next thing that we are going to do is to look at migration. What is going to happen when the switch is turned on? Now, what do I mean by that? Let's say we have a circuit here. And this is our electrochemical cell. In this case, the switch is closed. Now, if the switch is closed, it means that electrons are flowing across to move into the cathode where it will be gained. So the short side represents the cathode. Now, we should have a bulb in our circuit that is showing us that the light is coming on because the switch is closed. Whenever the switch is open, then our bulb will not be lit. So in this case, our ions, being positive and negative ions, are floating about our cell, moving around. But in this case, when you turn on the switch, then the ions would move towards a particular electrodes depending on the type of ion. That is migration. So if this is the cathode, it means that it is the negative electrode. And if this is the anode, it means that this is the positive electrode. So then, negative ions would migrate towards the positive electrode, while positive ions would migrate towards the negative cathode. But that only happens when the switch is closed and the electrons are now allowed to flow, where they will be gained at the cathode, reduction, as well as here the electrons or the ions would move towards the anode where they lose electrons, and that process is oxidation. So in our example, using aqueous copper 2 sulfate, our electrolyte here would be copper 2 sulfate, which consists of the ions Cu2 plus, H plus, SO4 2 minus, and OH minus. So the negative ions would be your SO4 2 minus and your OH minus, which would both migrate towards the positive electrode. And our positive ions, being copper 2 plus and H plus, both would migrate towards the negative electrodes. Now, which one would be preferentially discharged over the other? If you look in the electrochemical series, you will see that copper is below H plus. Hence, copper would come off in preference to H plus. You'll also see that OH minus is lower than SO4 2 minus. Hence, OH minus would come off in preference to SO4 2 minus. So looking at our cell, we'll see that our copper 2 sulfate is blue. Why is copper 2 sulfate blue? Well, copper 2 sulfate is blue because it contains copper 2 plus ions. And this ion is responsible for the blue color. So if we remove copper 2 sulfate, then our electrolyte will become less blue by becoming more pale. Now going back to looking at our ions, at the anode, OH minus and SO4 minus would migrate towards the anode. But OH would be preferentially discharged because it is lower in the series, hence will be more easily oxidized than the SO4 2 minus, and that would come off in preference. So you should observe effervescence at the anode. The long side of the battery is the positive side, which is the anode. The short side is the negative side, which is the cathode. So on this side we have the cathode, and on this side we have the anode. So the gas coming off at the anode is oxygen gas, and we can test for that shortly. As you can see, at the cathode, Cu2 plus is lower than H plus, hence Cu2 plus will be more readily reduced than H2, and it will form the atom copper solid. So copper solid should be observed forming around the cathode. So our observation is based on what is formed. In this case, you observe a pink or reddish brown solid, while at the anode you observe effervescence. Now, a point of note, OH minus ion is alkaline. So, if we use litmus paper and we place it at the anode, we should observe something or some form of color change taking place. So because OH minus is alkaline, we can use a red litmus to test for the presence of OH ions at the anode. Now, alkaline or base turn red litmus blue. So if this is alkaline, your red litmus should turn blue. In the case of a cathode, we are not really testing for the presence of copper because we can see that. But remember that H plus also migrated towards the cathode. So now the H plus that is around the cathode, it is acidic. So if you place now blue litmus, it should turn red. Acid turn blue litmus red, while base turn red litmus blue. This gas coming off here, which is oxygen gas, you can test for that gas. Now, oxygen gas should relight a glowing splint. So, if you place a splint that is glowing in the gas, then it should relight. So the oxygen will relight the glowing splint, and that is how you can tell if the gas coming off is oxygen. We don't have a gas coming off at the cathode, so we can't test for the presence of a gas there. But again, you can observe the red-brown solid. Now finally, in your conclusion, what can you say about your electrolyte? If you notice, you see that we are removing copper 2+. Remember we said that copper 2+ was responsible for the blue color in copper 2 sulfate? If we keep removing copper 2+, then our observation should be that the electrolyte will become pale. So these are all observation. Our litmus paper turning blue for the OH minus. In the case of H+, the blue turns red. You observe the relighting of a splint, of a glowing splint, and you observe the electrolyte becoming pale as the process goes on. So the longer the process, the more pale the electrolyte will be because the more Cu2+ you will be removing. Now you can make a general conclusion now about the electrolyte. Remember, we removed copper 2+ and we removed OH minus. Now Cu2+ and OH minus, they form CuOH bracket 2, which is copper 2 hydroxide, which is a base. H plus and SO4 2 minus, that is left, they form H2SO4, which is an acid. So removing Cu2+ and OH from the electrolyte, the solution now is now less alkaline and more acidic. So the solution will become more acidic because you remove an alkaline solution from it. So we just looked at aqueous copper 2 sulfate. Let's look at the electrolysis of aqueous copper 2 sulfate. This time, we are not going to use an inert electrode. We are going to use our active electrode. Please note the difference between the aqueous using inert electrode and the aqueous copper 2 sulfate using active electrode. Let's go. Using active electrode and our electrolyte is aqueous, then which factor are we going to look at? Well, it must be factor 3, which deals with the type of electrode. Now, the type of electrode being active here, this takes preference over the position in the series as well as the concentration of the electrolyte. So factor 3 takes preference over factor 1 and factor 2. If you notice in this cell, you'll see that the side that is the longest is a positive side. So this time my anode is on the right. The negative side is my cathode, and this time it is on the left. Notice electrons are being lost from the anode, hence the process of oxidation, while at the cathode, electrons are being gained, hence the process of reduction. Since the electrode is active, that is, copper electrode is placed at the anode and the electrolyte is aqueous copper 2 sulfate, then remember what we said would happen? If you're active, the anode would dissolve. So we'll form copper ions from copper solid. So the anode is breaking down into the electrolyte. As the copper atom form copper ion will now form copper atom and is built up around the cathode, as you can see here. So your observation should be the copper is dissolving or getting smaller in size. So you could say decrease in size at the anode, while you observe an increase in size. You should also observe that there is no color change in the electrolyte. Why? Every time you remove a copper 2 plus, which is responsible for the blue color, copper 2 plus ion is replaced into the electrolyte. So the concentration of copper 2 plus ions should be the same. As you remove, you put back, hence no color change. Remember, in aqueous copper 2 sulfate, using inert electrodes, we did not put back copper 2 plus ions as we remove them. So in that case, the electrolyte will become paler as you remove CO2 plus ions. So just remember, at the anode, dissolving is taking place, where the solid form your ion and disappears. While at the cathode, the ions are being reduced, hence it is built up around the cathode as it forms your pink solid. So your observation again should be your anode is dissolving while your cathode is being built up or increased in size. If your electrode is not copper, then you should observe your pink solid being formed around it. If it's copper, then it will already be pink or reddish brown, so you will just observe the increase in the size. So let's draw a before and after picture to ensure you truly understand what's going on here. So here we have our before diagram and our after diagram. Notice we have the positive side, the anode, this time on the left, and the negative cathode on the right. Our connecting wires, our electrodes are present. We have a switch, and the switch here is open, and we have a bulb here, and the bulb is off. The bulb is off because no current is flowing because our switch is open, meaning there is a break in the link between the wires. Now, if we should close the switch now electrons will be flowing. And electrons are flowing where at the anode, electrons are being lost. While at the cathode, electrons are being gained. So you'll see that at the anode, our copper solid is breaking down to form copper ion. And the copper ion that is dissolved into the copper sulfate electrolyte will be reduced and builds up around the cathode to increase in size. So you should observe that the anode is breaking down while your cathode is building up. And this has implication for some of the industrial processes that we will look at after looking at this topic here. So ensure that if you are active, your anode is a metal of the salt or of a soluble salt of the electrolyte. And you should observe that that is breaking down and the cathode builds up. So far, we've looked at the electrolysis of aqueous electrolytes using inert electrodes and aqueous electrolytes using active electrodes. Let's now look at electrolysis of a concentrated electrolyte using an inert electrode. Now, in looking at the electrolysis of concentrated sodium chloride solution, the important thing to look at here is that this word is concentrated. That means that we have a lot of the halide ions, Cl- present, and small amount of water. And the electrode is inert. So we can see that the ions present are Na plus and Cl- from the concentrated sodium chloride, and H plus and OH minus from water. Remember again that this will be in very small amounts, while this will be in large amounts. For migration, the two positive ions would move towards the cathode and the two negative ions would move towards the anode. You should remember again that the positive ions, the cations, you will treat those positive ions the same way you treat all ions that are aqueous and have inert electrodes. So we will use factor 1. So in this case, H plus would come off in preference to Na plus. Whereas on the anion side, the ions that move towards the anode, the Cl minus would come off in preference to OH this time, because it is more concentrated. So we have more Cl minus ions present than OH minus ions. So let's look at the reactions at the anode and the cathode. The reaction at the anode, you'll notice, is this side, because the long side of the battery is positive side. The short side is a negative side. So this is the cathode and this is the anode. And this is our sodium chloride electrolyte. So at the anode, Cl would come off in preference to OH minus. So Cl will be oxidized at the anode. So Cl minus ions form Cl2 gas. So what should we observe? You should observe effervescence at the anode. You should also observe a pale green gas. At the cathode, H plus is being reduced to H2 gas. So you should observe effervescence also. A very important thing to note is that when you have two gases being produced, the number of electrons lost must be equal to the number of electrons gained. And that will tell you which gas produces more effervescence than the other. In this case, the number of electrons lost is 2. The number of electrons gained here is 2. So the volume of both gases are the same. So we have one volume of Cl2 gas being produced at the anode, while we have one volume of H2 gas being produced at the cathode. So the effervescence is the same. In terms of the electrolyte, we removed H plus and we removed Cl minus. So we remove an acidic solution leaving Na plus and OH. So this is now going to make our solution more alkaline because we removed the acid from the solution. So in terms of your electrolyte, is now more alkaline. This example now is looking at the electrolysis of aqueous sodium chloride using inert electrodes. So if you look, you will see that we are either dilute or aqueous, and our electrode is inert. Therefore, we must be looking at factor 1. Now, the difference between this example and the one where we looked at concentrated sodium chloride is that this time OH minus would come off in preference to Cl minus because we have a lot of water to small amounts of Na plus and Cl minus. So being aqueous and our electrode is inert, then we must use factor 1. So first we must identify our ions, and then we must show migration. So you'll see that Na plus and H plus ions would migrate towards the cathode, while Cl minus ions and OH minus ions would migrate towards the anode. Then, if we're looking at factor 1, which is the position in the electrochemical series, we'll see that H plus is lower than Na plus. Therefore, H plus would be more easily reduced. In the anions, you'll see that OH minus is lower than Cl minus. Hence, OH minus would be preferentially discharged over Cl minus. Let's look at the reactions at the anode and cathode. At the anode, which is the positive side of the electrode, OH minus would come off in preference to Cl minus. So from that anode reaction, you'd see that O2 gas would be produced. Therefore, you should observe effervescence at the anode. H plus would come off in preference to Na plus. So you should observe effervescence again at the cathode. Now, you'll see we have two equations here. Why did we write two equations? Do you remember when I said that if you have two gases being discharged, then the number of electrons lost must be equal to the number of electrons gained? If I use this equation, the number of electrons lost here is 4, the number gained here is 2. So this is a bit deceiving in the sense that if you are doing an observation, this is saying that you'll observe the same amount of effervescence at both electrodes, which is not correct. Now, if you go by the rule that the number of electrons lost must be equal to the number of electrons gained, then if I have 4 being gained here, I'll have 2 volumes of H2 gas being produced. So here I have 1 volume of O2 gas at the anode, while at the cathode I now have 2 volumes of H2 gas being produced. So what is that saying? If I should draw my anode and draw my cathode here, at my anode I might have 1, 2, 3, 4 bubbles showing effervescence. Since I have 2 volumes at the cathode, I must have twice the amount of bubbles. So this is saying that we have more effervescence at the cathode and less at the anode. So in terms of your observation, looking at this equation, you cannot tell that you should observe more at the cathode. But remember, if 2 gases are being discharged, one at the anode and the other at the cathode, the number of electrons lost must be equal to the number of electrons gained. And you can observe that when you carry out your experiment, that you'll see that more effervescence will be at the cathode than at the anode. So 1 volume of O2 at the anode to 2 volumes of H2 at the cathode. In terms of our electrolyte, because we are removing water, our electrolyte will become more concentrated. So when you add water, you become more dilute. When you remove water, you become more concentrated. When you add an acid, you become more acidic. When you remove acid, you become more alkaline or more basic. So our electrolyte is now more concentrated because we removed water. So we see now the difference between carrying out the electrolysis of concentrated sodium chloride and aqueous sodium chloride, that the reactions at the anode and the cathode are different, and our observations are a bit different. The final type of electrolysis that we will look at is of molten substances. Now, molten substances is simply a solid that is melted. So it will be in the liquid form, not the solid form. And if you're molten, then you do not have any water present. Therefore, you would not have any H plus ion or OH minus ion present if you are molten. Let's check out this example. So in the electrolysis of fused or molten lead-2 bromide, we are using inert electrodes. So the only ions we will have present in our lead-2 bromide, the ions are Pb2 plus and Br minus. Because you are molten, no water is present. So only 2 ions. So what does that mean? The Pb2 plus would migrate towards the cathode and the Br minus would migrate towards the anode. The anode being the positive electrode and the cathode being the negative electrode. Let us look at the reactions taking place at the anode and the cathode. Here you see from this diagram that we have our flame, and our flame is melting the lead bromide. It is keeping the ions free to move about. Now, if I have my positive part here being the anode, then the negative ions, which is the Br minus ions, would migrate toward that electrode. And the positive ions, being the Pb2 plus ions, would migrate towards the cathode, the negative electrode. When they migrate there, they are not competing to be discharged because they are the only ions at the respective electrodes. So we'll see Br would be oxidized at the anode to form Br2 vapor gas. As you can observe, the Br vapor coming off here. So we have bromine vapor because the bromide ions lose electrons to form bromine vapor. And that is observed by your effervescence of your red-brown vapor. On the cathode side, lead would be reduced by gaining 2 electrons to form Pb. Now the lead form here will not be in the solid state because it is molten, so it will stay in the liquid state unless it is cooled, then it will form a solid. So here you'll have molten lead being formed at the cathode. So just remember, as long as you are fused or molten, you only contain 2 types of ions. And those are the ions present in the compound. No water is present if you are molten. So this concludes another of our lessons in our chemistry lecture series. The next time we meet, we will be looking at the industrial application of electrolysis, after which we will be doing calculations involving Faraday's law. See you then.